Hi, I'm Zor. Welcome to Unizor Education. So we continue talking about Hamiltonian. Previous lecture was an introduction, and today I will try to generalize basically whatever the ideas were presented, and that's why it's called General Hamiltonian. Now, this lecture is part of the course called Physics Plus. It's presented on unizor.com. The website is totally free. There is no subscription need, no advertisement, no sign-in is necessary. So basically it's all available for free for everybody without any kind of advertisement, interruptions, etc. Pure knowledge for your consumption. Okay, now every lecture has video and text presentation, and the text is basically like a textbook, so you can learn the theory from the notes for this lecture and the video in any sequence, and I do recommend you to approach any kind of a lecture from both sides. First you can watch the video presentation, then you can read the textual part of it on the same page basically, or in any other sequence. It's all for good. Now back to Hamiltonian. Now very brief repetition of what was in the previous lecture. First we started with Euler-Lagrange equation, which is dl by it's supposed to be a partial derivative by dqi is equal to d per dt. This is a full time derivative of partial derivative by velocity. Then we introduced, actually by definition, the generalized momentum, which is dl by dqi, which actually allowed to rewrite basically this, since this is now pi and full derivative by time. Usually we symbolize with a dot on the front, on the top, so the whole thing looks like dl by dqi is equal to pi dot, right? This is pi, the generalized momentum, and the derivative by time is this dot. Very nice. However, we have introduced one more variable, which is generalized momentum, but the number of equations is only n, so we have 2n variables and only n equations. So we proceeded further in the previous lecture, and we found out that considering Lagrangian is equal to kinetic minus potential energy, we have introduced function h, which is Hamiltonian, which is sum of these two, which is full energy of the system, and we came to another set of equations. One equation was like this, and another equation was like this. The only thing is there was a minus sign here because it's minus u, yeah, t minus ul. So in this case it's qi derivative. Now these are 2n equations with 2n independent variables, q and p, coordinates and momentum, and that basically seems to be a nicer system of equations than the one which is this one. This is the second order differential equation. These are first order, so we increase the number of variables, but we have decreased the complexity of each equation. Plus it looks much better. Okay, so that was last lecture. It heavily depended on this, how Lagrangian is represented as a difference between kinetic and potential energy, and then we have total energy of the system, and then we derived all these equations. So from this and this, we have derived this new system of equations. Fine, but again, we heavily depended on this, and this is not necessarily true. I mean, it's true for most of the simple mechanical systems, but whenever we want to, use this in much broader, much broader number of problems, theories, etc., and we do, and we will, this is not applicable anymore. Now, let's not get into why it's not applicable and what are those systems where it's not exactly true. But just trust me that the derivation of these equations was extremely helpful in those new cases when this is not true. So my purpose today is to generalize these things in such a way that it does not depend on the fact that Hamiltonian is actually a full energy of the system, and Lagrangian is looking as a kinetic minus potential energy. So I would like to generalize this thing and still come up with something like this, where H is something which is related to Lagrangian, related to coordinates and momenta, without relying on a specific way how Lagrangian and Hamiltonian look. So let's assume that we have a general system with some kind of a Lagrangian, but we would still like to come up with this and express H in terms of Lagrangian, coordinates, and momenta. So that's my task for today. All right, but how can I basically approach this thing? Well, I don't know the way the function H actually look. All I know that I have to have Lagrangian, I have to have all the coordinates and all the momentum, and somehow I have to mix them together to get this function H, which will, with these equations being true, actually. And obviously using the fact that Lagrangian and coordinates and their derivatives satisfy the Euler-Lagrange equation. So that's the general understanding of the whole thing. We completely put our problem from another actual angle. We approach our problem. That consider we have some Lagrangian which has the Euler-Lagrange equation satisfied, and Q and P, where P is defined like this. So this is it. I'm not really assuming this. This is not given. What's given is this, and I have to prove that this is true for some kind of a function H, which I must guess, if you speak. Well, guessing is actually kind of easy, and here is why. Let's basically talk about my assumption that L is equal to T minus U, and try to express H, which is T plus U, in such a way that it does not really depend on T and U, but it depends on Lagrangian and coordinates and momenta. So I have to somehow convert this into a different form, which is not really dependent on T and U. And if I will be able to do this, it would be a good candidate for H function in the general case. And then what I will have to do is I'll just check if the function which I have guessed from the previous assumptions, if I was able to express H in terms of L, Q, and P, and this new h is satisfied these equations, then my task actually is solved. So I do not present you, okay, h is equal to this, and present it as a function. I would like to first have it derived from whatever I know from some particular case, from a simple case, and then I will check if it fits the general case. Now, it will fit, obviously. So, how can I do that? Well, it's actually simple. Here it is. How can I express h, which is t plus u, in terms of Lagrangian? Well, Lagrangian is t minus u. So I can actually put it 2t minus Lagrangian, right? 2t minus t and plus u would be t plus u. That's simple, right? Now I have to express the kinetic energy in terms of basically q and pi. Well, this is actually not very difficult because, again, in my very simple formula for kinetic energy, it's sum of mass times speed square, right? Now, no, speed square is actually can be expressed somehow differently. This is mi times vi, which is pi, right? What's the momentum in classical physics? Mass times velocity times one more velocity. We have a square here. So what is velocity? Velocity is derivative of the coordinate, right? So that's basically how t looks. I mean, I have to put 1/2 here, sorry. So that's my t in classical mechanics. Well, so 2t is, will basically cancel this 2, and my good candidate for h is sum of pi times qi dot minus L. So this is the formula which depends only on coordinates and momenta, well, and derivative of coordinate, which is velocity, and Lagrangian. It does not really depend, this formula does not explicitly depend on kinetic or potential energy. So my question is this formula good for these equations? So is h defined as this thing, which I just guessed, no, not guessed, I used some particular case and came up with a formula which seems to be, satisfy my demand. So it does not depend on energy, it depends only on the Lagrangian coordinates and momenta. So I got this formula. Let me check. I mean, if it fits the bill, if it satisfies these equations, then there is absolutely nothing wrong with saying, okay, this is Lagrangian, and we can use it and solve this equation instead of Euler-Lagrange. So L is satisfied, or Euler-Lagrange equation, I know that. So from this formula and these definitions, let me put it on the top. So that's what's given basically now. H is equal to sum of pi qi dot minus L. So with this formula, this is given, and this is all given. So Euler-Lagrange for Lagrangian, definition of momentum, and this quite abstract formula which I have just invented based on some consideration. Now, this is given, this I have to prove. If I would do this, well, that means that my original problem, which is n equations of second order, can be actually solved with 2n equations with 2n independent variables, but the first order differential equations. Okay, now this is now quite straightforward, pure math without any kind of physical intuition or anything like that. I just have to check if these two equations are satisfied. All right. But here I would like to pay I would like you to pay attention to very important consideration. What are my variables right now for h? Well, this looks like another variable, but we have agreed that momentum and coordinates are functions. Okay? Now this is not really an independent function. It's the derivative of qi by time. However, that's not really you see, we have defined pi as such a derivative, but I would like qi to be treated qi with a dot, the derivative by time. I would like it to be treated as a function of independent coordinates, which are time, all q's and all p's. This is a very important momentum. P and q, momenta and coordinates, are independent variables, as well as time. And I do not actually want to say that derivative of coordinate is totally independent of anything else. I would like to treat it as another function of these arguments, which satisfies certain laws, obviously, but it's supposed to be treated as an independent function. That's very important. It depends of everything. Now, in a simple case, for example, of regular simple mechanical system, we know that momentum is defined as p times v. Well, v is actually q dot, right? So they are related in this case. Q dot is a function of momentum. So that's very important to understand that in this simple case it's just function of momentum. But in more complicated general case, I would like to maintain the possibility that it's actually a function of everything. That's the most general case, so to speak. I'm kind of making it a little bit more general, just to be sure that I do not miss any kind of dependencies which might actually be. Because again, I'm abstractly considering two n-dimensional space where p and q are n and n independent coordinates, which means everything else should actually be defined in terms of coordinates, momentum, well, and time. So it's actually 2n plus 1 dimensional considering the time. So this is a purely geometrical viewpoint, right? Okay, so we have basically established this. Now let's check this. Okay. Let me get some space. I will put dh by dpi should be equal to qi dot, and I will free my space here. So I have more room. All right. So I have to check this. All right. Well, let's start with this. So I have to basically check it for every I, but I will use I for summation here. So I will check it for I is equal to k in this particular case. So I will put k here, since it's just one particular coordinate. And I will use I for summation. Okay, fine. So, all right, let's start. dh by dpk equals to. Well, let's just look at this one. Well, first of all, this is a sum. Where is dependency on the momentum? Well, first of all, obviously there is one particular pair where this is pk and this is qk. and partial derivative by pk of this particular thing is just qk, right? With the dot. Now, but all functions of these, all members of this summation have qi, and qi, as I was saying, with the dot, is a function of t, all the p's, p1, p2, pn, and all the q. So there is a dependency on this as well. So I have to add sum of pi times derivative of this by pk, which is I have to derive partial derivative of qi by dpk that would be a full derivative of this sigma. So this is a product, so it's n different products. One particular component has to be used twice for this one, but all of them are supposed to be containing this one. So it's this times partial derivative of this should be everywhere. But whenever I'm doing partial derivative of this times this, it's only one, because everything else, which is where I is not equal to k, then that zero out. And minus dl by dpk. Now, the derivative by dpk is not just itself. Again, L depends on T, P, and Q, right? So, just get a little more. L depends on T, Q, and Q dot. That's our original Lagrangian, right? Now, this is dependency on pk is here within the Q dot, because there are all different p's here, including the pk. But all of them contain this. So basically I have to put here not just one, I have to put sigma by dq I with the dot times dq dot I by dpk. This is a chain rule, right? So we have many different q's here, q1, q2, q3, etc. And there is a dependency on p in each one of them. So that's why I have to differentiate by each qi. This is the sum by a, by each qi, and then from this qi with a dot differentiate by pk. This is the chain rule. Am I right? Let me check. Yes, looks like I'm right. Which is equal to qk with a dot plus sigma pi minus dl by dqi dot times dqi by dpk. Right? This is dpk and this is dpk. It's a common multiplier. So I put p minus dl by dqi dot in parentheses. Now, what is this? This is the definition basically for pi, so it's 0, which means the whole thing is equal to q k with that, which is exactly this one. So we have proven, even in this complicated case when the velocity depends on all the independent variables, all the coordinates and all the momenta, I still have this thing satisfied. All right, let's check the second one. It's basically the same thing. Once more. dh by dqk is equal. Okay, this is what it is. Now, where is dependency on qk? Here. It depends on all the different q's. So we actually have to really do all of them. All right. So it would be sum pi times dqi dot by dqk. All right. Yes. So p is independent on q, so it's just a constant multiplier. So all the dependency on qk is here, and that's why each one of them should be like this, sum by I. Okay. Now, how about here? Here we have two dependencies. Q depends on qk, and q prime and q dot depends on qk. So I have to really again do it as a multifunctional derivative. One thing is partial derivative by q itself. Okay. And another thing, whenever I'm doing uncovering the q from the q dot, would be the whole sigma dl by dqi dot times dqi dot by dqk. Let me check. Yeah, that seems to be right. So what's here? Well, look, this one and this one have dqi dot by dqk as a common, so it should be equal to, now this is separate, so this one minus dl by dqk plus sigma pi minus dl by dqi dot times this, sorry, times this. Same thing here. This is 0. So I have only this. Okay. Now, what is this? Look at this. Minus. This is the same as this. It's Euler-Lagrange equation. Now this is pi. So derivative by time from pi is pi with a dot. And that's exactly what should be proven here. So but we have proven that both equations are satisfied in case we have defined our Lagrangian as such and where momentum, generalized momentum, is defined as this. So from Euler-Lagrange equation, from definition of momentum, and our intelligently guessed expression for Lagrangian, and thinking basically that P and Q are independent variables, and even the derivative of coordinate, the velocity, is a function of all of these coordinates. This is the most general case. In all these cases, if this is given, we have this Hamiltonian satisfying these equations. Now, what I'm actually thinking about, if we are talking about equivalency of both approaches, Euler-Lagrange equation or Hamiltonian equation, we have to really prove the backwards as well. So if the Hamiltonian equations are satisfied, where the Hamiltonian is this, will the Euler-Lagrange equation be satisfied? Well, that's basically the same thing with the before, just I'll just write it differently. So dH by dqk, as we know, it's equal to minus pk dot, right? We assume this on one hand. On another hand, let's just think what it is. If we will differentiate it by qk, this is the derivative of q1 would be here, so that's sigma pi times qi dot by qk. That's what it is, because p is constant, independent of coordinate, minus, and here we also have the same thing basically, dl by dqk and minus sigma dl by dqi times dqi by dqk. Same thing, right? But now what happens if I assume that pi and dl by dq, that's the definition, so these two, it's the same multiplier here, go out. So what we have right now, we have that dH by dqk is equal to minus dl by dqk, and this is, as I was saying, minus pk dot. So that's what we actually came up with. But what is this? Both are minus, can be pluses, right? Now dot is actually d by dt, right? And pk is by definition dl by dqk dot, by definition. And what is this? This is the Euler-Lagrange equation. So if we assume that Hamiltonian equations are correct, then we basically have derived Euler-Lagrange equation, which basically now we have both ways. From Euler-Lagrange we derived Hamiltonian equations, from Hamiltonian equation we derived Euler-Lagrange equation. So these two are equivalent, and this one is a generalized definition of Hamiltonian. Hamiltonian as a function is represented from Lagrangian and independent coordinates, and momentum in this particular formula, which we have semi-guessed. I mean, we just derived it in a simple case and maybe decided, okay, maybe it will fit the bill. And it did fit the bill, which we have proven. So we basically have an expression for Hamiltonian, which is this one. In many textbooks, they just give you this formula and then check that this is actually satisfied the equations. I decided that it's much more kind of natural. How did we get this? We just basically, somebody guessed it the first time, and how did he guess it? Well, probably the same way I was just trying to explain. They saw that in a simple case, that's what it is, and they have decided, okay, let's check, maybe it works in a general case. And so it did. Okay, so now this is a generalized expression for Hamiltonian without any kind of relation to the energy, or without any relationship to expressed expression of Lagrangian as a difference between kinetic and potential energy. It's a very, very generalized formula, and that's what I wanted to derive today. That's it. Now, I do suggest you to read the notes for this lecture. Again, the whole lecture is, you go to unizor.com, go to Physics Plus course. The chapter is Hamiltonian. So the first lecture was introduction, and this is the second lecture in that chapter. That's what it is. Thank you very much, and good luck.